But in many cases, often large amounts of data are available, but no labels are present. For example, medical devices such as a CAT scanner, MRI scanner, or an EKG produce streams of data, but these are entirely unlabeled. They do not contain the information of which part is indicating what disease. In these cases, obtaining labeled data is difficult, costly, or impossible, and so supervised learning methods are not possible. This gives rise to unsupervised learning. Unsupervised learning describes a family of algorithms that learns patterns from unlabeled data. This is in contrast to supervised learning techniques, where a model is given a training set of inputs and a set of observations, and must learn a function from the inputs to the observations. In unsupervised learning, only the inputs are available, and a model must look for interesting patterns in the data. The machine is forced to build a compact internal representation of its given input data, and use such representation to complete the requested tasks. The two main categories of unsupervised learning we will be discussing today are anomaly detection and clustering. One widely adopted use case for unsupervised learning is anomaly detection. It is generally understood to be the identification of rare items, events, or observations that deviate significantly from the majority of the data and do not conform to normal behavior. Looking at the graph to the left, most of the data points follow a nonlinear increasing line. The one exception is the point at 36,000. This point deviates significantly from the pattern of the rest of the data and would be considered an anomaly. One example of the use of anomaly detection is with fraud. With the common use of credit cards, financial fraud has become a major problem. Unauthorized or fraudulent transactions can sometimes be recognized as a break or an anomaly from the user's normal pattern of usages, such as large volume transactions or rapid buying sprees. Credit card transaction data can be fed into an anomaly detection algorithm in the form of a vector, which is a collection of numbers such as transaction amount, transaction time of day, transaction location, and time since the previous transaction. The outliers can then be flagged to the bank as potentially fraudulent. In these cases, the bank can either unilaterally block the card or request the user to authenticate the transaction in another way. Anomaly detection algorithms, however, may not always be accurate. Sometimes, a normal data point may be flagged as an anomaly, a false positive, or an anomalous point is mistaken as normal and overlooked, a false negative. For example, when looking at cancer diagnoses, a false positive would be if cancer was detected in a patient that does not have cancer. A false negative would be if cancer was not detected in a patient that does have cancer. These inaccuracies can have consequences. In this situation, a false positive would cause unnecessary stress and worry for the healthy patient. A false negative would be far more damaging, as a sick cancer patient may not seek treatment, mistaking themselves as healthy. A false positive, however, is not always the more damaging error. In addition, the severity of errors is not always the same. A false negative COVID test is less serious than a false negative cancer diagnosis. It is important to assess the situation in which an anomaly detection algorithm is being applied to. The algorithm can then be adjusted to favor a false negative over a false positive, or vice versa. The end goal of an anomaly detection algorithm is to be as accurate as possible, while also minimizing the risk/cost of false results. Clustering is a machine learning problem that aims to group data that have similar properties or features. Recall the previous medical imaging example. Often large amounts of data are given, but no labels for the data are given. Doctors have a large amount of imaging data, but they do not know whether the obtained images are associated with what kind of disease. In 2019, a team of researchers in the UAE, Egypt, and Australia conducted a meta-study of clustering algorithms on Alzheimer's disease data and reported that it was possible to identify subgroups which corresponded to the stage of the disease's progression. A number of clustering methods have been applied to datasets. They found that all of the clustering algorithms investigated brought a new level of insight into the various subtypes of Alzheimer's patients. The clustering techniques allow medical practitioners to identify patterns across patients that would otherwise be difficult to find by eye. The blue dots on the left diagram represent all of the input feature vectors. The separate green, blue, and red dots on the right diagram represent these same inputs, but now they have been grouped into 3 separate clusters. You want the clusters to be distinct from one another, while also having individual data points within a cluster as similar as possible. In other words, you want to maximize the distance between clusters and minimize the distance between each data point and its average point of the cluster to which it is assigned. This is the goal of clustering problems.